This is part 2 of lecture 9 of Logika računalništvu, logic in computer science. And in this part, we're going to look at a professional piece of software, a freely available software, which is a model checker that, amongst other things, does model checking for properties of transition systems expressed in linear time temporal logic. This is the same model checker that's referred to in the course textbook. The version I'm going to be using is slightly more modern than the course textbook, so some of the syntax has changed since the course textbook. It doesn't really matter because for this course you certainly don't need to do anything like learn the syntax of the new SMV, as it's called, model checker. The purpose of the lecture is rather to illustrate for you, to demonstrate for you how one can use such a model checker. Now, actually, I'm not very well versed in this piece of software, so what I'm going to do is relatively simple, but anyway, hopefully it will nonetheless be sufficient to demonstrate the kinds of things one can do. So if we go to the Emacs window over here, what I've written here is a model in the modeling language of the new SMV model checker. Now, for me, the modeling language of the new SMV model checker is, I don't really understand the principles that have been used to design it. I find it rather puzzling to use, and it seems to be very restrictive in some ways. But nonetheless, I've written here a model which is a description of a transition system. And it's a transition system, again, for the same computer science problem we've been looking at throughout this part of the lecture course, namely mutual exclusion, because that's a good example for transition systems. So here I've got a description of a mutual exclusion algorithm. Only to make it a little bit more interesting, I'm going to mutual exclusion for 3 processes rather than 2 processes. If the modeling language were easier to use, I would have done for many more processes than 3, but 3 processes was enough writing for me. Okay, so what this text file here, which is, as I say, written in the modeling language, defines is it defines a transition system where the states of the transition system comprise of states of 3 processes. So we've got process A, process B, and process C. And each of these 3 processes, A, B, and C, has 2 variables down here and under var. It has, maybe I'll move the black square down to the bottom, that's just the cursor. So it has a state variable. So each of the processes A, B, and C can be in 3 states. So it can be running, that's what we called non-critical before. Trying to get access to the shared resource, and critical if it gets access to the resource. And each of the processes also has a scheduler that can take the value A, B, and C. So we've got 3 each state has 3 processes. So each state of the transition system, we've got a slight confusion here in the use of state, and we're going to talk about states of the transition system. The state of the transition system consists of 3 processes, each with their own state. So the state of a process is given by either its run, try, or critical, and the scheduler value. So each process can take 9 values. There are 3 processes, so that's 9 cubed potential states that we can form from this data. So that's quite a lot of potential states. But there's going to be an initial state, and in the initial state, all the processes start off in run, and the scheduler, all the schedulers for process A, process B, and process C start off with value A. So let's go to the board, and we're going to start to write the state of process. So I'm going to begin to draw the transition system. Of course, I'm not going to draw all the transitions, because all the states, because there are too many of them. But so the initial one is run. In fact, let's just use RRR. So run, run, run. And the scheduler is, so this is process 1 has state run, process 2 has state run, process 3 has state, process A, process B, process C has state run, and the scheduler of each of them, process A has state A, scheduler A, process B has scheduler A, and process C has scheduler A. But in fact, the schedulers are always going to have, there are 3 schedulers, but they all have the same value. So I'm just going to write the scheduler value at the end here. Let's maybe tell you what, I'm going to use capital letters for the run, and right, so this is run, 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 scheduler A. So let's go back to the Emacs window, to the editor. So you might wonder why I have one scheduler for each process if they're always going to have the same value. Well, I did that just because I'm not very well versed in the NuSMV modeling language. So this was the easiest way I could manage to do things. But we're going to see that the scheduler always has the same value, the schedulers for each of the 3 processes. We've done the initial state, so the important thing is the transitions that take us from one state to another, and that's going to allow us to, we're going to gradually expose the transition system by going along the transitions. So the transition system is specified by, we define the next state from the current state, and we do that by, so for each process we're defining the next state of the process. So at the moment in our transition system, we were in the state run, 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 and with the scheduler A, and so if process A is in the state run, and the scheduler is process A, because this is process A looking at the value me. So at the start we say process A, its value me is little a, and we're saying that its 2 other states are process B and process C. So process A, it's useful to have these values to refer to the scheduler value that refers to process A, which is of course little a, and the fact that and the states of the 2 other processes. We'll use those in a moment. So this says if we're in process A and we're running and the scheduler is A, then we can move then process A can move either to run or to try. And we read this for each of the 3 processes. So if we're in process B and the state of process B is running and the scheduler is B, then we can also move to run or to try. And if we're in process C and the state of process C is running and the scheduler is C, then we can also move to process C to run or try. So if we go back to the picture, this means here each of the three states is running, but the scheduler is at A. So that means that, so that means that process A, that's the first running component here, process A can either stay running or can move to try. So we have, and process B and process C, for that we do need to go back to here. So then there's the second line, so this one's executed only if the first line didn't execute. So the default is if this test didn't satisfy, if these constraints were not satisfied here, if the constraints, so if the state, so for process B, these constraints, and process C, these constraints will only be satisfied if the scheduler is B and C respectively, whereas it wasn't in our state. So for process B and process C, when the state is run but the scheduler is something different, then they need to stay at the value with the value run. So going back to here, that means this state can evolve to can either go to trying, these two need to stay the same, or all three stay as reading, because only the process A state can change, and the process A state must either stay as reading or go to trying. And I want to go back to, and the scheduler, well, the scheduler always, for each of the processes, as I say, the scheduler is always going to take the same value for each of the processes. The schedule always moves from A to B, from B to C, and from C to A. So, sorry, I didn't mean to close that. I want to go here. So the scheduler always goes from A to B to B to C to E. So this can go like this. And we have a loop also from here to R, whoops. So all three processes still reading, none of them changed, but the scheduler has moved to B. Now the scheduler is B, so the scheduler is scheduling which process can change its state. Now it's B, so from here we can either go to, so B can possibly go, process B can go into the trying state, and now the scheduler changes to C, or again this can stay, all the processes can stay in the running state, and again the scheduler goes to C, and once it's at C, that process, the scheduler goes back to A, and from here process C can evolve to trying. So here we have R trying, and again the scheduler goes to A in this case because it goes from C to A. And for example, from this process here, we've got that here process B is scheduled, so this might go into the trying state, the trying, this one stays as running, and now, whoops, now we go to the scheduler gets augmented to C. or this one might stay in the same, this one might stay as with process B as running, in which case we would go to TRRC. And so on. And you can see there are going to be rather a lot of states from here. One possible move is that, well, here process C is scheduled, so that might also go to trying. And then the scheduler goes back to A because it was at C. And here we're in a state that all three processes are trying for the critical, are trying for the shared resource, and process A is scheduled. So let's go back to see what happens. So when a state is trying and is scheduled, so in this case process A is trying and is scheduled, then it can stay trying or it can go critical, but of course it's only allowed to go critical if the resource is available. And for the resource to be available, that means that the two other processes must not be critical. So the condition for being able to go critical is that for a process, say process A, to be able to go critical, is that process A is currently trying, process B and process C are not critical, and the scheduler says it's process A's turn. In that case, it can go critical, but everything's as non-deterministic as possible, so it also might stay trying. If you're trying and you're not scheduled, or if one of the other processes is critical, then you can't leave the trying state, so then you stay as trying. So that means if we go back to our diagram, so from here, from this state, process A is scheduled, it is trying, neither of the other two processes are critical, so this one can go critical. Process B and process C stay as trying, and of course the scheduler goes from A to B, rather. But this process can also go from, even though A is scheduled and it would be able to get the resource, it might not be given the resource, so then the scheduler just moves on to B, and from here it's possible for process B to go critical, so T, C, T, and then of course the scheduler moves on to C. Or again, the process might stay trying, and then we go to T, 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 C, with now C is scheduled. Again, we've got to loop back here. And from here, process C can go critical. So this goes critical and the scheduler goes back to A, and so on. And I think that's quite enough of the picture. As you see, it's reasonably large. This is not a huge transition system by the modelling standards, but I think we've seen enough of it. Or maybe maybe we could just see just a tiny little bit more that without going back to the file. I'll just tell you then, of course, we can always stay in the same state, so the scheduler will just move on from B to C, and then we can again stay in the same state, so then we'll get back to the scheduler back to A, and once we're critical and we're scheduled, so process A is critical here and is scheduled by the scheduler A, then if we go back to, So if we're critical and we're scheduled, then we can stay critical or we can go back to the running state. So we might stay critical for some time, but eventually we can, once we're scheduled, we can relinquish the resource and go back to the running state. If we're not scheduled and we're critical, then we need to stay critical. We always need, in order to move, we always need to wait for our turn according to the scheduler. And so if I go back to here, so from this point, at this point we can go back to running, and then we've still got these processes B and C are both trying, so we can go back here to running, trying, and the scheduler moves on to B. So all this business with the scheduler is a bit fussy. The point is it just allows us to move one of the processes at a time, and I've implemented it like that because the default in SMV is that the model's asynchronous, which means all the sub-processes make their moves. They can all move simultaneously. They all have to move basically simultaneously as each other. And then that would lead to further complications in a mutual exclusion model, because you might have the resource available and all the processes jump onto the resource at the same time. So I'm not allowing that possibility by making sure that only one process moves at a time. Of course, it depends what the actual situation you're modeling is. This might not be a very accurate model for some situations, but anyway, its purpose is to illustrate a computationally interesting model for being able to explore what we can do with it with a model checker. Okay, so I've now talked you through the model. Let's go back to the text file for it here. So that's the model. Let's go to NuSMV, so let's launch it. I'm launching it in, so I've just got it in some random directory, so I haven't set a path for it. That's why I'm accessing it in this funny way. Doesn't really matter. I'm going in interactive mode so we can interact with it, and I'm loading this in exclusion.smv file, which is this file here that I've got on the left. So we do that, and then we say go. That means go to the model that we've loaded, and then we say pick state, which means pick an initial state. Actually, we've already specified here what the initial state is, but in general, one would just give in the file some constraints on the initial state, and then we would pick one state from it. Okay, so now what I want to do is explore the model a little bit. So actually what I want to do is go to another Emacs window. So here I've got some, so we've done go and pick state, and now what I want to do is simulate a random run from that state for 100 steps. There we are. So I've done that. I've simulated a random run for 100 steps, and well, it's told me it's successfully simulated the random run. So that's not very interesting because we haven't seen it. So after a simulation, we can ask to have a look at the traces of the simulation, which will tell us the traces are like the paths that were the execution paths that were navigated during the finite execution paths that were navigated during the execution. We've just simulated one run here. So if we show traces, we're going to see one trace of 100 steps. So there we are. That's quite a long thing, of course, because we're going through 100 different states. If we go back to the beginning, so first state, the state we started in, was everything was in state run. All the 3 processes are in state run, and the 3 schedulers were all A. As I say, the 3 schedulers are always the same, but indeed they are. Then we go to run, and we're all in B, and the scheduler is B, so we haven't changed the state. And then B goes to try, and the scheduler moves on to C. So we can have a look at our picture we've drawn when we find it. So we started here, run A, we went to run B, and now we've gone to run, try, run in with the scheduler in C. Now I didn't draw any further transitions out of here, so we're going to go off my picture, but I think you can imagine how things go. So let's go back to the terminal that we were in. So then we stay in run, try, run, and the scheduler just cycles round. And then we went to try. So we've got 2 processes trying. Let's see if one of them is going to go critical. Still 2 processes trying. Still 2 processes trying. Still 2 processes trying. Okay, process B has gone critical now. Process B has gone critical, and it left. Fortunately, we didn't ever get 2 processes going critical at the same time, which is the mutual exclusion we want to avoid. And this one's been reset and it's gone back to run, and so on. And then we've got, that was just like 12 steps through. We go a long way down. We got process A's gone critical there. Now process B's gone critical again. And now process C. Anyway, it doesn't really matter. We don't want to look at this 100 steps, so 101 state to run in so much detail, in any more detail. But what we can do is, explore the model a bit more. We've just looked at 100 step run from it. So one thing we can do is we can ask. Well, we worked out that there were 9 cubed possible states, in the sense that there are 9 cubed ways of different values, 9 cubed different sets of values we can set these variables to. But we know that not all those states can be reached from the starting state of the transition system, because, for example, the scheduler always takes the same value. So that really means that there are 3 to the power of, so that would give us only 3 to the power of 4 states, which is 81. But in fact, there are fewer states than that we can access using the rules. If we go back to the rules we had for moving from one state to another, so the exclusion. So using these rules, we could continue drawing the transition system and the states we can get to, and until eventually we've exhausted all the states we can reach from the starting state. Maybe I should just draw an arrow into the starting state let's put it in purple like I was doing before, just to make it clear that that's a special arrow, that's the starting state. So there's a question, how many effective states are there in this model? How many states can we actually reach from the starting state? So you can try to work it out for yourself if you like, if you understand the model. But an easier thing to do is to ask NuSMV that. So I don't remember the command, so let's go back to the this file properties. We say print reachable states. Okay, so it tells us out of the, as we saw, 9 cubed, or it likes to put things in exponents of 2, so 2 to the power of 9.5 and something. Anyway, out of the 9 cubed possible configurations that we get from setting all the values of the variables, actually only 60 of them are reachable. So this is not really a large transition system by model checking standards, but it's much larger than a transition system we would like to actually draw on our board. So we wouldn't want to complete the picture that I started drawing. Okay, anyway, what we want to do is we want to check some properties of the model. So so to do that, we're going to, you can check properties using various different logics. There is NuSMV supports LTL, linear time temporal logic, that we've been studying. It also supports CTL, computation tree logic, which is a different temporal logic that's also covered in the course textbook, but we're not going to do it we're not going to cover it in this course. LTL is the one that tends to be used in applications. So we can check an LTL specification using the property that we state. So what I want to do is just check, it was kind of obvious from the model description, but I want to check that the scheduler is really consistent across the processes. That is, for all states, it really is the case that we can reach. It really is the case that the process A's scheduler is equal to process B's scheduler value is equal to process C's scheduler value. So we put the property in quotes, we check the LTL spec, and there we are. It tells us, so it performs a model checking algorithm. Actually, it's not the one based on Bookie Automata that we did in lectures. It's a different model checking algorithm, but nonetheless, it's still a model checking algorithm. Obviously, it's related because they're all basically doing the same thing, and it tells us indeed this property is true. That's not a surprise, but it's a sort of sanity check on the model. It's checking that the model is like a sensible model to begin with. So let's check something we're really interested in computationally. So we want to check the important safety property that only one state is critical at a time. So this is the whole point of mutual exclusion. We want to check that mutual exclusion is really true. So, I just realized that, I basically said, we'll check this property, and I didn't talk you through the property. So we wanted to say the scheduler is consistent across the processes. The scheduler has the same value in all processes. So we say globally along the run, it is the case that 2 atomic properties hold. So the AND is the conjunction here, conjoining the 2 atomic properties. And notice that our atomic properties are actually, we've got a nice language for expressing interesting atomic properties, but from the point of view of LTL model checking, this is just an atomic property that we check, and it is the property of a state that says that is true when the scheduler value for process A is equal to the scheduler value for process B. And this is the atomic property of the state that is true when the scheduler value for process B is equal to the scheduler value for process C. So we're saying globally, so we were checking that along every run, it holds that globally along the run, the scheduler values of the 3 processes are all the same. In other words, in every reachable state, the 3 scheduler values are all the same. But now we want to check the safety property. So we want to say that only one state is critical at a time. Now, I'm going to do this in the following way, that I'm going to say globally along a run. So if you've got a run, globally along the run, it's going to be the case that whenever process A is critical, then it's not the case that process B is critical, and it's not the case that process C is critical. This is not quite the full safety property, because the full safety property would also need to say that if process B is critical, then it's not the case that process C is critical. But nonetheless, we can imagine those other properties will hold by some sort of symmetry property because the model is defined in a perfectly symmetric way. This is giving us some information we want, that if process A becomes critical, then it's never critical at the same time as either process B or as process C. And once again, we want to check that globally along every run. So at any point in time along any run, if process A is critical, then process B and process C are not critical at the same time. So let's copy this property over to our window. So again, well, I want to do the check LTL spec minus P quotes, copy the property. And again, this is true. So jolly good. Our model really does enforce mutual exclusion. Let's go back to the model and try and understand for ourselves why that is the case. So go back to the model, mutual exclusion, and really the reason is this, is that in order to transition for a state, one of our processes, A, B, or C, rather, to transition from the try state to the critical state, it needs to, this is the statement that it does it. It can only do that if the other, on the condition that the other two processes are not critical. And because the processes are only acting one at a time, only when they're scheduled, only one process can make that transition at that point. So one process gets in there, it becomes critical, and then it'll be, while it is critical, while that process is critical, it will be impossible for the other two processes to become critical. Okay, so we can understand that, but you know, when you see the model written like this, one could easily make a mistake in how it's written. So it's good to verify that really it is the case that the model does satisfy this property. So let's go back to our properties here. So now what we're going to look at, we've looked at safety, so now let's look at liveness again. So the same liveness property we've been looking at for mutual exclusion before. And this is saying whenever a process gets, one of the processes gets into the trying state, eventually it will become critical. So something good eventually happens. Of course, the full liveness property would say this not just for process A, but also for process B and for process C. But once again, we're just going to be interested in checking that it holds for process A, and because the model description is perfectly symmetric, it should likewise hold for process B and process C. So let's check this property. So if process A, so whenever process A gets into a try state, at some point further in the future, it is guaranteed to become critical. Aha! So this time, and not surprisingly really, given this is a similar situation to what happened in the first lecture of this part of the course, so that was lecture 7 when we looked at mutual exclusion. So the liveness property is not guaranteed to hold. Let's see. So we've got a counterexample. This is going to be one of these lasso paths of the kind that we saw in the lecture. So we're starting in the starting state, run, A, or run with the scheduler at A. And we see that then it goes to try. Process A goes to trying. So we're now in the condition that process A, we're now in the antecedent of the implication here, process A is trying, and we want to see, so presumably this run is going to then, process A has got into trying, but it's never going to be the case that in the future process A becomes critical. So process. So notice all this trace gives us is it just tells us the values that change from one process to the next. So from going from here to here, process B and process C stayed in the value run, but of course all the schedulers changed from A to B. Here they're going to change from B to C, but process A, we're not being told that process A's state has changed, so it stays in the trying state here. Process B is now gone into trying, and then we go around the scheduler A. The scheduler changes A, B, C, and that's it. So what we have here, notice that it says a loop starts here, and that means this is the first state. So our lasso, this is the starting state. This is the first state we get to from the starting state, then the second state. This is the first state of the loop. We then go to here and to here, and this last state it displays is the same as this one. So that's NuSMV gives you the first state of the loop also at the end to sort of emphasize that you're going back to here. So we've gone from the scheduler C, A, B, C, and actually basically it's a very boring reason that that process A started trying here and it never got out of it. So process B has also gone to trying. That's completely irrelevant to what's happening. It just happens to be the case along this particular lasso. The process B is trying. Essentially, no state has gone critical. We've simply gone round a loop. Both A and B are trying. They stay in the trying state, and we simply go round a loop where we stay in that state, and only the scheduler is changing. Let's see if we've got this one on our picture. So we've got A is trying. And B, and so this state is in our loop where A and B are trying and C is still running, and the loop is going from here to let's go back to black. So the loop is going from here to TTRA, TTRB, and then back to TTRC, like that. That's what the loop is doing. And basically, I think the loop was this. So process A started trying, process B started trying, and then we ended up going round here. So basically, we're getting stuck in a loop where two processes are trying, but nothing ever goes critical. So we're going to try and understand the model better by seeing that a reassuring liveness property does hold under appropriate fairness constraints that say if we're in a situation in which something repeatedly can go critical, then it eventually will go critical. So let's go back to the terminal, or actually let's go just down to the properties. So what we're going to impose now are some fairness constraints. So the main fairness constraint, perhaps I'll start with the complicated formula, is going to be that this formula. So GF remember, well, GF says it's globally the case, it's always the case that at some point in the future, so for any state in the future, there will be some further point in the future along which this holds. In other words, it says this property holds infinitely often. So GF's an important construction in temporal logic to say something holds infinitely often. And actually, here we've got a property that's an implication. And what it's saying is that if we're infinitely often in a state of the transition system in which process A is trying and there's no good reason that it should not get the resource, so obviously it should not get the resource if process B, if either of process B or process C were critical, but if infinitely often process A is trying and process B at those infinitely many times is not, neither process B nor process C are critical at those infinitely many times, well then that would be jolly unfair on process A not to allocate it the resource. So instead we do allocate. So what we want to do is say that if that happens infinitely often, then indeed it does get allocated to the resource, and indeed it gets allocated the resource infinitely often. So for any particular time that we're trying, we might wait, process A is trying, we might, for any finite number of steps, we might have to wait even though the resource is not in use, but nonetheless eventually we will have to, if the resource is not in use, eventually we will be allocated it. Okay, so that's so that seems a reasonable constraint to have. And we also want to ensure that when a process gets the resource, when it becomes critical, it doesn't get stuck there forever. So to ensure that, we're going to have three properties. One saying it's infinitely often process A is not critical, so that's saying process A does not get stuck being critical, so it does not get into the critical state and stay there. Similarly, process B does not get into the critical state and then stay there forever, and also the same for process C. And what we're going to do is we're going to prove that as long as none of the processes, we make the fairness assumption that no process hogs the resource forever. That's hogs here is an English word meaning basically lays claim to the resource and keeps hold of it forever. We don't want a process to do that, so there's a perfectly reasonable fairness constraint that none of the three processes can hog the resource forever. And at the same time, we also want to make sure that if process A tries to get the resource infinitely, and it's doing that infinitely often in states at which it could indeed be given the resource, then it will indeed be given the resource those infinitely many times. So what we're going to check is whether these fairness constraints, the conjunction of all these fairness constraints, is enough to give us the liveness constraint. So to do that, we check a big implication, and there should surely be a way in SMV to give these fairness assumptions names and say assume these named assumptions and then check under these assumptions, but I'm afraid I don't know the software that well, so I'm just going to wrap everything up in one big implication here. So this is just the conjunction of these four statements implies the liveness property, this big implication here. So I'm just going to cross that over to the window and see what we get. First let me copy the command, check LTL spec bit, and then so we want to follow that up with this very long implication. And copy that. quotes there, and then we shall see what happens. Oh, and there we go. The property is indeed true. Okay, so hopefully from that rather brief look at things, with a brief look at checking LTL properties with a not particularly large model, you've got some flavour of how these things are actually done. Let me just make one assumption about these, one comment rather, about these kind of fairness assumptions. So a good question here would be, well, if we're allowed to make the fairness assumption, we don't get stuck in the critical state, why can't we just as well make the fairness assumption we don't get stuck, process A doesn't get stuck in the tri-state? And if we made that assumption, then this liveness property would be trivial. If process A doesn't get stuck in the tri-state, then it'll have to get out of the tri-state, and the only way of getting out of the tri-state is to go into the critical state. So it will certainly be the case that whenever it's in the tri-state, it at some future point becomes critical. So a question like that would be a very good question, but there is actually a difference between this assumption we don't get stuck in a critical state and we don't get stuck in the tri-state. So if we go back to looking at the model, so if we look at the critical states, we can always get out of a critical state when the scheduler comes round to us. And since the scheduler cycles, it will eventually come round to us. So if we're in a critical state, we're always going to have the possibility of being able to get out of the critical state. So really, the assumption we don't get stuck in a critical state is just that eventually we make use of the possibility that is given to us to exit from the critical state. And that's a perfectly reasonable assumption. Whereas with the tri-state, we cannot make such a reasonable statement, because the tri-state, we can only get out of it if the other states are not critical. And it's not reasonable to say, well, if we're in the tri-state, we can assume that we don't want to just say we can assume that the other states will not be critical, because then we're not exploring properties of the model. And if we make that assumption, we're trivializing the whole issue of liveness here for the for this particular model of mutual exclusion. So the point is, it's actually difficult to get out of the tri-state because it depends on the status of the other processes. So it's not reasonable to make the assumption that we don't get stuck in a tri-state, because we might very well get stuck in a tri-state if the other processes got stuck in critical states, although of course they can't get stuck in critical states, but we have to make sure that simultaneously that not only do they not get stuck in critical states, but somehow simultaneously the resource they get out of it so that the resource becomes free from us. So the property is really a little bit subtle, and the assumption we did make which is that we become critical if we are infinitely often given the opportunity to. That is a perfectly reasonable one, because it's not making assumptions about the other states. It's just saying if we happen to be in the circumstances that the other states are in the right position for us to become critical, then we will make use of the opportunity that we have been given. Okay, so the last point I wanted to make is, so this is obviously a bit of a toy example. It only had 60 states. I'm not really in a position to demonstrate much larger examples because I don't know this software that well, but nonetheless, this kind of technology for model checking of LTL properties has been put to important uses in industry, in particular for checking properties of hardware design. So this has become actually a mainstream part of hardware development, checking certain properties of circuit layouts that involve properties a bit like mutual exclusion and other properties. And so LTL and this kind of verification is an important tool in that area. Right, so that wraps up today's lecture. I hope, as always, that you're all well, and there will be, so I think next week there will be something a little bit different from the usual lecture, but I shall contact you about that nearer the time. Anyway, that's enough for today, so bye for now, and if you do have any questions, please send me an email. I'd be happy to receive one. Okay, bye.